Dear colleagues, good afternoon. So the title of my presentation was already told. Just a moment. So distributed denial of service or DDoS attacks are very important threats to network security. These attacks can cause severe disruptions by flooding the system with malicious traffics. Among the various distributed denial of service techniques, flooding attacks such as SYN flooding, ASK flooding, HTTP flooding, and UDP flooding are very difficult to neutralize because they mimic legitimate traffic. These attacks exhaust service resources, making them unavailable to legitimate users. So machine learning is one of the fundamental technologies that can be implemented in various fields of science and technology. In cybersecurity, machine learning is a very important tool that allows to detect and prevent various types of threats. Traditional methods such as rule-based system and statistical approaches are not capable to detect complicated and sophisticated attacks. The use of machine learning allows to analyze network traffic more efficiently, to detect anomalies and classify malicious traffic. And this makes these methods indispensable for modern information security systems. The purpose of this research was to develop a methodology to detect and classify DDoS attacks, namely SYN flooding, ASK flooding, HTTP flooding, and UDP flooding, using neural networks, as well as to evaluate the effectiveness of the proposed neural network model when applied in conditions close to real-world one. A neuron is an information processing unit that is fundamental to the functioning of a neural network. The diagram in the figure shows a model of a neuron that is a basic unit for a neural network. In this study, a neural network with a multi-layer perceptron 24165 architecture was proposed. This model has three main layers. The input layer contains 24 neurons, which corresponds to the number of features in the input data. The hidden layer consists of 106 neurons with a hyperbolic tangent activation function. The output layer comprises 5 neurons, which correspond to the number of classes in the classification task, including normal traffic and 4 types of DDoS flooding attacks. The activation function was chosen as softmax. On this slide, you can see a typical architecture of multiple layer perceptron with one hidden layer and one output layer. The dataset that was utilized in the study was designed to detect DDoS flooding attacks. It has 2 categories of traffic: normal traffic, which represents legitimate user activity, and malicious traffic, which was generated by various types of flooding attacks. In the process of training of the neural network, the dataset was divided into 3 parts: training, testing, and validation samples. The total sample size was more than 38,000 records. Of this, 16,619 records were normal traffic, 3,556 records were SYN flooding, 7,562 records were ASK flooding, 1,044 records were HTTP flooding, and around 10,000 records were UDP flooding. 70% of the data was utilized for model training, 15% were employed for validation, and another 15% for testing. The model evaluation was based on 4 main categories of classification results: true positive, true negative, false positive, and false negative. Based on these values, several key performance indicators were assessed: accuracy, precision, recall, specificity, and F-score. In the test data set, the 24,165 neural network correctly classified most of the samples. but it is noticeable that classification errors happens between normal traffic and SYN flooding. The similarity in the nature of the queries between normal traffic and SYN flooding is the main reason for the increase in the number of classification errors. The performance of the neural network on the dataset is given in the following table. As it can be seen from the table, we have very positive results and very high accuracy, precision, and recall, and F-score for all the DDoS flooding. So these metrics are more than 99%, which confirms good classification results. Practical testing of the neural network, a special network infrastructure, which was based on Oracle Linux and KVM hypervisor, was created. Virtual machines running parrot security generated distributed denial of service traffic, while normal traffic was created using laptops connected via Wi-Fi. The network packets were captured with the TCP-DUMP tool and analyzed by using a specialized Python program, so a specific Python program which was written for this purpose to extract traffic features. A total of 10,564 traffic records were created, of which 3,845 were normal traffic, 1,721 were SYN flooding, 2,203 were ASK flooding, around 1,000 were HTTP flooding, and around 2,000 were UDP flooding. The proposed MLP neural network showed good performance in classifying traffic from the lab environment. Also, it was not 100% perfect and made a number of errors, especially when classifying SYN flooding and ACK traffic, because, for instance, SYN flooding traffic is very similar to legitimate traffic, so it is hard to distinguish between them. In general, the network detects all types of distributed denial of service attacks very well. So you can see the confusion matrix of neural network in practical testing. When the model was tested on the data from the lab environment, performance was also quite high for all types of attacks. In this table, you can see key performance indicators of the neural network, 24, 106, 5 in practical testing. And conclusions. So to sum up, the neural network showed high efficiency in detection and classifying distributed denial of service attacks. The overall accuracy is more than 95%, and the precision, recall, and specificity scores are also quite high for all types of attacks, which indicates the high reliability of the model. For all types of DDoS attacks, the overall F-score is 96%, which indicates that the model is highly balanced. This means that the model can effectively detect true attacks without generating a significant number of false alarms. So thank you for your attention.